Gone live. We can verify the stream picks up here in a second.
I see it on the stream.
Hello, and good morning, everyone. My name is Sarah Johnson, and I'm a university lecturer at Simon Fraser University. And I would like to welcome you to our special event as Saturday Morning Lectures has not only moved online, but turns 16 years old this year. In 2004, partners from Triumph and UBC met to create a science lecture series geared for high school students. Since then, approximately 230 talks have been given to over 10,000 Vancouver, British Columbia area residents. A whole generation of high school students and members of the public have had the opportunity to hear about physics-related research at the cutting edge. And hopefully, many of the students will have been inspired to pursue further studies and careers in the areas covered by these lectures, ranging from medicine to earthquakes and the workings of our universe. We're now excited to be scientists without lecterns, opening up these talks to the world online. Today's speaker is Brandon Stuart. Brandon started his post-secondary studies at Kwantlen Polytechnic University, and he started out in accounting, but then he decided that accounting really wasn't his thing. So he instead pursued an engineering transfer certificate. And from Kwantlen, he transferred over to the University of British Columbia, UBC, where he earned his bachelor's degree in engineering physics. Brandon is now pursuing a PhD in physics, specializing in condensed matter. One of the reasons he decided to go the physics route instead of the engineering route was because of a co-op experience he had at the Max Planck Institute in Stuttgart, Germany. Brandon also did a physics co-op at Triumph as well. So during Brandon's talk today, the live chat in YouTube will be open. So please ask any questions you have about today's talk there. We'll compile all of the questions and spend the last few minutes together discussing them live. So please welcome Brandon to this inaugural Saturday morning lecture online event. Today, Brandon is going to tell us all about how we can see atoms.
Thank you very much for the kind introduction, Sarah. I'm just going to bring my screen up here. All right, perfect. So yeah, as Sarah mentioned in her nice introduction, I'm going to describe the techniques and instruments that I use during my PhD in order to visualize atoms. I'm going to come out right away and just tell you the device we use. It's called a scanning tunneling microscope. And the easiest way to think about this and to explain how it works is to break this down into its three components, which of course are scanning, tunneling, and the microscope part itself. Now, in order to properly explain this, I found that it's best to go in sort of a reverse order. So my talk is going to be outlined as followed. I'll begin talking about the microscope and sort of the history and how they work. And then I'll jump into exactly what tunneling is and how it makes this a device quite a bit different from an ordinary microscope you might be used to using in, say, high school. And finally, I'll have a quick blurb on scanning, which is, again, one of the key defining features that separates this from most devices you might have used in the past. So just to jump into exactly what microscopes are and sort of a history of them, I have a bit of a scale bar down here. Now, this is different from most scales you might be used to, say on your ruler at home or something, in that each increment is actually 10 times smaller or 10 times larger than its previous counterpart. And this is called a logarithmic scale. And since the birth of humans, really, we've been able to see things on this scale up to about 60 micrometers or so. And this includes things like a typical child, a bumblebee, which is about a centimeter large, and all the way down to human hair, which on the lower end of things gets us right down to the limit of what the human eye can see. But beyond this, for many thousands of years, humans couldn't see anything smaller than this. But it was always a goal. We always wanted to see if things could be broken down into smaller and smaller things. And this is where the microscope comes into play. So in about the year 1600 or so, the optical microscope was developed, which allowed us to push our boundaries of what we could see to approximately 200 nanometers. And this allowed for things like bacteria to be seen, for example. Here is my favorite bacteria, lactobacillus. It's what gives the sour flavor to things like sauerkraut and sourdough. But beyond this, you had to go to different techniques. So an optical microscope works by using light, and it had a fundamental resolution limit of about 200 nanometers. Beyond this, the scanning electron microscope was developed in 1937, and this increased the resolution that we could achieve by about a factor of 100, allowing us to see things on the order of 2 nanometers. A typical example of this would be some silicon electronic devices, like you might find in this the computer you're currently watching me on, or your phone. And seen here is a scanning electron microscope image of the transistors that make up your devices. But beyond this, it still didn't quite get us to the atomic level that we wanted to achieve. And for many years, people truly thought that this might be impossible. And that was up until about 1981, when the scanning tunneling microscope was first developed. And this finally gave us the resolution to observe atoms, which appear on about a 0.1 nanometer size scale, or more commonly referred to as an angstrom in my field of study. Now, beyond this, we don't really have much. We have some modifications to STMs, which allow us to increase the resolution ever so slightly, but we have yet to get a completely different device. So for the past almost 40 years, this is the best we can do. But who knows in the future, maybe we can improve our resolution even more, and maybe somebody listening to this talk can be at the forefront of that research. So how exactly do typical microscopes work? And I'm going to start this by explaining how an optical microscope works. These have a series of lenses. In the most simple case, it'll just be 2 lenses. And you look through this on one side using your eye. And what this does is it takes a small object. So for example, this red ladybug here, and it deflects the light that comes off this ladybug in a certain way that almost tricks your eye into thinking that the ladybug is much bigger than it actually is. Now, similar, but still different in its own ways, is the scanning electron microscope, or even the transmission electron microscope, that operate under similar principles, but using electrons instead of light photons. Now, these techniques have fundamental resolution limits. In the case of an optical microscope, it's basically half of the wavelength of the light that you're trying to look at. And this leaves us with a resolution limit of about 200 nanometers. Going to the electron microscope, a similar thing happens, but rather than it being limited to the wavelength of light, it's limited to the energy of the incoming electrons. Now, this also has a fundamental resolution limit, and as I mentioned, it's about 2 nanometers in size. So in order to see things much smaller, we actually had to look at a completely different way of zooming in on things. And this is where the scanning tunneling microscope comes in. And with that, I'm going to describe exactly what tunneling is and how we can use it to properly visualize atoms. So in order to best describe what tunneling is, I'm going to use a cartoon picture. And you can think about it like this. Pretend you have a brick wall here, like so. And on one side of this brick wall, you have a baseball pitching machine. And on the other side of this wall, you have a baseball player. Now, there are 2 types or 2 branches of physics you can really think of. The first is classical physics, and the second is modern physics. Classical physics is basically everything you learned in high school, and obviously a little bit beyond that, but it dictates that if you were to fire baseballs at this wall, no matter how many times you did it, the baseballs would always just bounce back towards the pitching machine. Unless, of course, you gave it enough energy to just blast through the wall and create a giant hole. Now, modern physics encompasses everything that classical physics doesn't describe, and a large portion of that is quantum mechanics. And tunneling itself is a fundamentally quantum process. So if we switch from a classical physics picture to a quantum mechanical picture, well, I guess really nothing much changes. Most of the balls still fly towards the wall and bounce off. But the key difference here is that most of the balls do it, not all of them. There are some baseballs with a small probability that will actually just go right through this wall like it wasn't even there and hit this baseball player. And this is the fundamental process that allows us to visualize atoms. So how exactly does that work? This clearly doesn't translate right now into an atomic level picture. Well, this is due to wave-particle duality. Basically, what happens here is a particle, say an electron in this case, has the ability to behave as both a solid particle, like a baseball, or like a wave at the same time. So much like how, say, sound waves can travel through walls and you can hear a TV in another room, or how light waves can travel through your windows and allow you to see what's outside, this wave-like nature of the electron allows it to pass through things that classical physics says are impenetrable, like that wall. So translating this into an actual STM, there are pretty much two main components you have to think of when you look at one. So see here, you can see this is about a nanometer scale down here, and each of these purple circles represents a material surface that I want to look at. And in my field of condensed matter physics, this is called a sample material, or just a sample for short. And then these gray circles up top are the atoms that make up the tip of an STM, and the tip is what we use in order to image these atoms. Now, how this works is we bring this tip and this sample extremely close together, on the order of maybe a single atom or around a nanometer. And in doing so, we apply a bias voltage, and this allows some electrons to tunnel from the sample material into the tip. So relating this back to my baseball example, in this case, the yellow electrons that I have drawn right here would be the baseballs. And the space between the sample and the tip, this vacuum area, would be the wall. And classically, like I mentioned, electrons would not be able to jump from the material surface to the tip unless they were given a sufficient amount of energy. But obviously, like I mentioned, in a quantum mechanical picture, some electrons are able to just jump between. So what we can measure from this is the number of electrons that are going from the sample to the tip per second. And this gives us what's called the tunneling current. So how do we actually use this phenomena to observe atoms? Well, we need to add a couple more components that make this possible. First, we need to be able to position the tip very precisely on the material surface. We do this using piezoelectronic devices. So a piezoelectronic device is something that changes or shifts in a certain way, say expansion or contraction, when you apply a voltage to it. And it's very precise. You can apply voltages such that your tip can be positioned with sub-nanometer resolution, which allows you to scan across a material surface. One nice thing about this is the tunneling current itself is very dependent on the size of this, or the distance between your sample and your tip. It's so dependent that you can actually measure a distinct difference in the current when your tip is placed directly above an atom versus when it's placed in between two atoms. And this large dependence on this height allows us to sort of view our atoms. And we can, again, like I said, move around the surface using these piezoelectronic devices. Now, obviously, the tip and the sample are much too close together to be able to position this using your hand. You need to use the aids of computer-guided softwares. So this piezoelectric device is connected to a controller. Here I have the proprietary controller we use in our studies. And then this is connected to a computer. So what I do is I basically sit at the computer and I tell it, I plug in some numbers, and it translates this into various voltages and currents and tells the tip precisely where to go on the material surface. So how exactly does the computer actually get the tip so close to the sample so that we can actually measure our current? So it uses, like I mentioned, this piezoelectric tube. So when we apply a voltage to this piezoelectric tube, we can expand it, and as a result, move the tip further down, and in this case, towards the sample material. So if we put one of these sort of sideways on a stack of piezoelectric motors, so these piezoelectric motors actually move the piezoelectric tube along this direction. And we have a sample here at the end of it. And what we do is we apply a voltage to the piezoelectric tube, and as a result, it expands and tries to look for the sample. In this case, it wasn't close enough, so it wasn't able to hit the sample, so it contracts back up, and then the piezoelectric motors move it closer towards the sample as a whole. We once again expand the piezo tube, and it once again does not reach the sample. So it contracts once more and takes another step towards the sample. We're now close enough that when we expand the piezoelectric tube, the sample and the tip become close enough to achieve tunneling, and our computer program tells us that we can begin the next part, which is scanning. So speaking of scanning, what happens is once we get to the material surface, so here we have our material and its atoms, and the tip is now sufficiently close to achieve tunneling, we can scan across the surface and observe the individual atoms. The way this works is, and here I have a little graph to show how this is going to work in a second, where Z is the height of the tip and X is the position of the tip with respect to the material surface. And like I mentioned before, the tunneling current that we measure is extremely dependent on the tip sample separation. So what we can tell the computer to do is to maintain a constant tunneling current. Then what happens is as the tip is moved across the surface, when it's in between two atoms, it's actually going to move towards them because it has a larger separation distance and the current has dropped, and we have told the computer to keep the current constant. So I have a little animation to show exactly what this looks like as we move the tip across the surface. And you can see that it starts moving and it kind of follows the profile of your atoms. And then in the side graph I've shown here, you can see that it results in a single line that traces out the corrugation of your atoms. This is great and all, but this still doesn't really get us to see atoms. Instead, we're just seeing a single line profile. So what we have to do is take many, many single line profiles to create a two-dimensional image. And that's what this next slide is going to describe. And this sort of single tip pixel by pixel image is one of the main differences between this type of microscope and a microscope you might use, or even a camera you might use on a day-to-day basis, say in your phone. So in your phone, the detector of the camera is similar to this. It's a bunch of pixels, but when you take an image, all those pixels are set off at once because all the detectors can be individually accessed. With scanning tunneling microscopy, we only have one tip, so we have to do this pixel by pixel, and this is what we call scanning. So the way this works is we bring the tip to the very first pixel of our predefined image. And from this point, we measure the height or the current or whatever we want to measure for our image. And we get one single data point. We then move the tip to the next pixel, and this is done by the computer program. I don't have to do this by hand, thankfully. But at the second pixel, it takes another data point. Then it does it at the third one. And then it does this for the entire top line. So this is exactly what I showed in the last slide. The tip has moved across the surface in one line. Then it moves down to the next line, takes another data point, and then does this again for the entire line. So now we have two lines stacked on top of each other. And it does this for the remaining lines in an image. It takes a while. It takes a little while. Taking an STM image can take anywhere from a couple of minutes upwards of a couple of days, depending on the measurement you're doing. But in principle, the same thing occurs. The tip moves back and forth across the sample, taking constant data points. And what you have seen here is a very zoomed in image of a single atom. Okay, so that sort of concludes the cartoons and the theory of how we can see atoms. I want to show you what this looks like in real life. So this here is a Createch STM. Createch is the company who designed and built it for our lab. And you can see it's rather large. The uppermost point right here at my mouse is about 3 or 4 meters high. And I'm going to just go through and point out a few key features here to describe what they do. So marked here in green, we have our STM cryostat. And what this does is it holds cryogenic liquids, in my case, liquid nitrogen or liquid helium. So liquid nitrogen allows us, or liquid nitrogen and liquid helium, allow us to get to cold temperatures and study the physics of our materials at a variety of different temperatures. And sometimes as you go into colder and colder temperatures, you come across phase transitions where the electronic property changes. Similar to how water undergoes a phase transition when you cool it down, it becomes ice. Similar things happen to our materials, but rather than physical phase transitions, the electronics change drastically. And in this case, we can get to approximately 4 Kelvin using these devices, using these liquids. To more basic terms, it's minus 269 degrees Celsius, which is colder than anything that you will find naturally on Earth. Below this, marked in red, we have the actual STM itself. You can't quite see it right now because it's inside this chamber, but if you look through this window, you'll see the STM, and I'll show you what that looks like on the next slide. But this STM is connected directly to the cryostat so that it can get to these nice cold temperatures that I mentioned just a second ago. Marked here in blue is our preparation chamber. So this is where we put the samples that we want to study before we transfer them into the actual STM. And it allows us to modify them in certain ways to achieve the goals we want in our experiments. And lastly, and maybe one of the most important things aside from the STM itself, is our pumping system. So within this chamber, we pump out everything, all the air, all the water, to achieve an ultra high vacuum. To put it into numbers, it's 13 orders of magnitude better vacuum than the atmospheric pressure that you're currently in. And this allows us to study our materials for an extremely long time without them becoming damaged. So if you look at certain materials like copper, for example, it will develop rust, or sorry, iron, sorry, it'll develop rust over a long period of time being exposed to air. Similar things happen to the materials that we study in the system, so we need to make sure that they stay away from anything that might damage their surface. All right, so I mentioned that if you look through this window, you'll see what the STM actually looks like. So what I did here is I put a optical microscope image taken from the side, and if we zoom in, you can actually see this STM tip and sample junction quite clearly. So this is magnified by about 10 times. The reflective surface you see at the bottom here is a copper sample. And you can see that it's nice and shiny, which means it's quite metallic. And then you see here the STM tip I described before. This is made with a mixture of platinum and iridium, and we use some acids and bases to form this nice sharp tip. Like I mentioned before, beyond the optical microscope capabilities, we have scanning electron microscope capabilities, and I have an image of what our STM tips look like under these as well. You can see the scale here is 25 micrometers, and this allows us to really zoom in and see just how close this tip gets to the sample surface. You can see the shadow of the tip right here. And this is almost into a tunneling regime, but not quite. All right, so that concludes sort of the first half of my lecture, describing the ins and outs of how an STM work and providing some background theory to hopefully help you understand it. I now want to take a bit of a pivot and talk more about what everyday materials look like on the atomic scale. So I'm going to do this using the periodic table of elements, everybody's favorite little table. As you can see, there are 118 different elements currently known to us. There's probably more that we haven't found yet, but 118 is what we have here. And with this, it doesn't seem like a whole lot of potential materials to study, but a lot of these materials combine together and form compounds. And when you do this, you have a pretty much endless supply of materials that you can study. Just to put some into perspective, I'm going to go through some materials that our lab alone studies. This begins with copper, just an elemental metal that's very common in everyday life. And in a few slides here, I'll show you what this looks like atomically. Beyond this, we have some compounds like iron selenide. This is one of the more recently discovered superconductors. I think it's about 12 years old now, which is extremely new in a physics point of view. Beyond this, we have the material I completed most of my PhD on. This is zirconium silicon telluride, and it falls into also a pretty new class of materials called topological metals. These were only discovered about 5 years ago, actually, so really pushing the forefront of physics research. We also have something called yttrium barium copper oxide, more commonly known as YBCO. This is one of the first high temperature superconductors that was discovered, and it was studied extensively in our lab for decades. And lastly, just to show you how complicated these compounds can actually get, we have this material that is studied by a research associate in our group. And this is just to show you that there are truly almost endless numbers of materials that can be studied just based on the periodic table. So to start, I actually want to study or to show you what one of the most common materials in our day-to-day life looks like, especially now with the technological age. And this is silicon. So silicon is used in every electronic device, and it makes up the building blocks of the electronic devices. So it creates, or all the transistors in your devices are made using silicon. It has pretty much the perfect electric properties to allow us to create these transistors. So this here is what silicon looks like in a single crystal form. So this entire cylinder is one solid crystal of silicon developed or grown in the aptly named Silicon Valley. And it's quite incredible what they can actually do with these silicon crystals now. They're grown to a purity of 99.9999999%, which means that for every billion atoms of silicon, there's only one defect atom, which is incredibly interesting. There's no other material in the world that can be grown with such a purity as silicon. And what they do with these giant crystals is they cut them into thin wafers, like you see here. And then using some advanced fabrication techniques, they can pattern in the transistors and create the devices that you use on a day-to-day basis, for example, the CPU in your computer. But this doesn't really show us what they look like atomically, of course. So if you were to take an STM and look at one of these silicon wafers, you could see something that looks like this. So each one of these little dots here is a single silicon atom. And you see that on the surface of this sample, the silicons like to arrange themselves into these beautiful hexagonal, almost flower-like patterns. We call this silicon 7x7. It's a special phase the silicon likes to organize itself in. But you can see that this is a very clean material. There's very little defects, and all the atoms are grown. They look almost exactly the same. So moving forward, I want to talk about another type of material that you use in your everyday life, even if you don't realize it. And this is copper. Pretty much all the wiring in your house or any sort of connecting cables you use will be done using copper wire. You can see here, this is a typical copper wire that you might find in an electronic device. But beyond this, it has some pretty interesting atomic properties. And further than that, it was also used as the main component in a penny up until about the early 2000s. So if you were to zoom in to the surface of this penny using an STM, you might see something that looks like this. So each one of these little dots is once again a copper atom. And you can see it looks a little bit different than the silicon that I showed you before. And this is typical of most materials. They have their own sort of atomic configurations that they like to go into. In the case of copper, it just likes to jam as many possible atoms as it can right next to each other to create this pattern where you can't really fit any more atoms. And you can see that it creates these little triangle patterns. Copper is also a little bit different than silicon in the sense that you can't quite grow it to the same level of purity that you could for silicon. And this can be seen in this next image of this next STM image of copper I have here. This is obviously a very old image taken from a textbook that I use in my studies. But you can see that each one of these little dips here, it almost looks like you threw a rock into a pond, for example. It has some ripples around it. Each one of these dips is a defect atom in the copper. I believe it's actually a molecule in this case. It's carbon monoxide. And you can see what it looks like. So it creates these sort of uneven surfaces, and it affects the way the electrons behave. Furthermore, whether by design or just by nature, copper also generally tends to have what are called step edges, which are these large cliff-like features here. This is what happens when an entire layer of copper atoms has been stripped from the surface of the material, and it results in these fancy-looking step edges. And you can also see the ripple pattern here, which is the electrons behaving and interacting with the step edge in a unique way. All right, so that was two examples of everyday materials that are used in your electronics. But what do not so everyday materials look like? These are materials that are studied more for fundamental research properties rather than being used in everyday devices. And the first one I want to show you is the material I did about 90% of my PhD on, zirconium silicon telluride. So this is a material that consists of elements, so zirconium, silicon, and tellurium, that are quite common. Honestly, you could probably find all of them in your backyard, but they don't really like to form compounds together. So while you might find them individually, I would almost guarantee you're not going to find zirconium silicon telluride in your backyard. And in order to create this, we need to use some very precise laboratory conditions and some very high temperatures. And when you complete that, you end up getting single crystals of this compound that looks something like this. So they're very small. Each side here is about 1/2 of a millimeter. So you can just imagine how precise and tiny this is. And then they're black and very reflective. So this is what it looks like. I have this under an SEM as well, just to show you in a bit more clarity what these surfaces look like, because the optical microscope is a little blurry. This one has a scale bar here. You can see 200 micrometers. So this is about 1/2 a millimeter. Now, this material has a pretty unique crystal structure. It looks something like this, where all the oranges are zirconium atoms, the blues are tellurium, and the yellows are silicon. And we can fabricate this in such a way that within our STM, we can actually remove a layer right between the orange atoms here, right between the zirconiums. And what remains is a very flat, pristine layer of zirconium. So what this looks like under an STM is something like this. And you can see, like I mentioned before, each one of these little bumps is a zirconium atom, and it likes to form a square lattice in this case, which is different from the copper and the silicon for that matter. So you get this perfectly square corrugation. Furthermore, you can see that like copper, it has a lot of defects, even more so than copper. And in this case, many different kinds. So in this case here, where you have this hole almost, that's exactly what it is. It's just a missing zirconium atom, something that didn't grow, and was a defect of the crystal growth process. And beyond this, you also have ones that appear very bright, and this might be a zirconium atom sitting on top of the surface. And you can see just by looking at this, there's about 5 or 6 different unique defects, and all of them have unique electronic properties. You can also see here, this is the first time I've shown you the specific energy that this scan or this image was taken at. And that's just a contrast to another scan that was taken at a different energy. And you can see that the material surface looks completely different. And STM is quite a nice tool for this, because you can actually manually set the energy you take your scans at, and you can sometimes access completely different physics on the same materials. So you can see that the defects look different, look completely different in the two images, which signifies that we're looking at different physical features, or different electronic physics, I should say. The last material from this periodic table that I want to show you is very similar to zirconium silicon telluride. It's bismuth antimony telluride, in the sense that they're both of this new class of topological materials. But this one looks quite a bit different than zirconium silicon telluride. And you can see here that rather than growing in these nice flat layers, it's quite mountainous. It almost looks like a topograph image of the Rocky Mountains or something like that. And zooming in even more, you can see this more clearly. The way this material likes to grow is by sort of spiraling out these step edges, like I explained in copper, and creating these mountainous terrains. So why did I show you these everyday, or I should say not so everyday materials? Like what use does this have? Well, just to explain one thing here, silicon is sort of reaching its fundamental limit for how good of a device you can make. We're already making transistors that are on the order of approximately 10 nanometers, which is very small. I think the fundamental limit is around 7 nanometers. But what this means is that if we want to make better devices, we can no longer make them smaller. We're going to have to go larger and larger and larger. And that's not something we want to do anymore. I mean, our phones now are already quite large. Personally, I think they're too large. And even my computer graphics card is taking up a large chunk of space. So scientists and researchers all around the world are looking for new branches of physics that we can use to make electronic devices with. And one of the leading candidates is these topological materials. Now, that's not to say that zirconium silicon telluride or bismuth antimony telluride is going to be the next silicon. That would just be trying to oversell this way too much. But it is a possibility that there are new physics that come out that allow us to make devices that we can use in an everyday environment. So some of these leading candidates, like I said, are topological insulators or superconductors or various liquids even that we can hopefully use one day in our everyday life. So beyond the periodic table, it's still on the periodic table, but beyond elemental compounds, I want to talk about a couple of more interesting things you can do with STM. In this case, it's looking at something called PTCDA. This here is a red dye. It's used. I actually don't know what the dye is particularly used for in practical applications, but at an atomic level or a molecular level, it looks something like this. And what's nice about this is it's an organic molecule. So for somebody who's never seen this before, all these H's are hydrogens, all these O's are oxygens, and then these hexagonal features in the middle, at each vertex you have a carbon atom. So it's just made of three elements. And using some modifications to STM, you can actually image the intra-atomic bonds of these molecules. So just to show you exactly what you're looking at here, because it might be a little hard to compare, I have a red outline drawn around these 5 internal carbon hexagons, and that's what lines up with this feature here. So what is interesting about this? Why do we care about these organic molecules that are just red dyes? Well, it turns out that if you put a bunch of these together with a couple of other molecules, they have photovoltaic properties, which means that they take light and they convert it into electricity. Now, you've probably heard about this through things like solar panels. You see them on the roof of people's houses now. It's becoming more and more common. The problem with modern solar cells and solar panels is they're large, they're very clunky, they're very heavy, and they're inflexible. You can't really do anything with them. So what's nice about these organic solar cells is that, one, they're flexible, which means you can put them on a wide variety of things and you don't have to carry them around or make sure they stay flat. Two, they're quite lightweight. They don't have this huge bulky characteristic of a typical solar cell. And 3, which I think personally is the most the coolest thing about them, is they're mostly transparent. What this means is you can put them on, say, the window of your house, and they won't block much of the light coming through. In fact, I think they only block 1 or 2%. You wouldn't really even notice it. So in reality, you could coat your whole window in these organic photovoltaic cells and create electricity without even knowing it's there. So this is where the application I think is really neat. The problem is it's kind of inefficient right now. So a lot of research is being done to increase the electric production from these molecules. And then lastly, I want to talk about the atomic manipulation properties of an STM. So this slide here is a little bit more just showing off, but somebody several years back at UBC was able to take an STM and spell out UBC using individual atoms. So each one of these yellow mountains here is a single atom or molecule. I actually think it's carbon monoxide, if I'm not mistaken. And he was able to take his STM tip that I described earlier, pick up these carbon monoxide molecules, and then drop them very precisely on the surface of the sample. Now, this obviously doesn't have too much practical applications, just being able to spell things, but it does have applications in atomic memory or something like that. So you can actually create very, very small memory using atoms. Now, this technology is years and years away from being anything you might see in your house, but it's still cool that you can actually manipulate atoms on such a fine level. And just to show this one more time, IBM came and created a video, the world's smallest video, titled "A Boy and His Atom." And it was taken with an STM. I'll let it play in the background. It's about a minute long, and then I'll describe sort of what's going on as it plays. So let's just make sure this works. Yeah, okay, it's running. So yeah, you can see here that each one of these little dots or balls you see here is a single atom, and the folks at IBM were able to pattern them in such a way that they could create almost like a lifelike figure. Now, I mentioned before that sometimes these STM scans can take an extremely long time, on the order, I mean, from anywhere from a couple of minutes to several hours. So you can just kind of take an idea of how long it would have actually taken to make this video. This probably took people months. So I'll just let it finish up here. So that's pretty much just showing what you can do with an STM, even if it's not super practical for any sort of research purposes. Now, just for the last couple of slides here, I want to talk about the lab that I'm part of. This is the UBC Laboratory for Atomic Imaging Research, or UBC LAIR, which is pretty aptly named considering we're located in the basement. The building itself is located in about the dead center of the UBC campus in the Brimacombe building. UBC LAIR itself is part of the Stuart Bluesen Quantum Matter Institute, which specializes in quantum research. And we share the building with the Advanced Materials and Process Engineering Laboratory. And it's actually quite an interesting building for research because things are being studied at all size scales. So on the large end of things, some of the people in the in AMPEL, the Advanced Materials and Process Engineering Lab, are studying things as large as airplane wings, whereas we are studying things as small as atoms. And it's quite interesting to see just the large size difference in the research that's being done here. The building is not quite open to the public right now because of coronavirus, but once this goes away, hopefully you'll be able to come and check it out. We have a few displays that you can see some of the research we do in the front lobby, and maybe even get a tour of the lab. So the lab itself looks something like this. We have 3 of these separate rooms, which isolate the instruments themselves from any sort of physical vibrations or noise coming from electricity or sound even. And you can see inside each one of them is an STM. So this guy right here on the right is the STM that I use, this Createch one. We have another one here from Omicron, and the one over in the far left is a home-built STM that will hopefully really push the boundaries of what an STM can actually study. And in each one of these rooms, the instruments are sitting on these concrete blocks, which are floating on top of some air springs. This completely removes, or not completely, but almost completely removes any physical vibrations you might experience, because in order to create to complete our measurements, we need to have this tip and sample very close, like I mentioned. And in order to do that, we need as little vibrations as possible. So this large hexagonal one on the left side here weighs in at just over 80 tons, if I'm not mistaken. The people that I work with, the supervisors, I should say my supervisors for my PhD, are Doug Bond and Sarah Burke. Doug focuses mostly on high temperature superconductivity and topological materials, as well as some microwave measurements. So you can see here, floating superconductor. And Sarah focuses more on those organic thin film electronics I described with the photovoltaic devices earlier, as well as topological materials and really improving STM techniques in general. Here's the lab I'm a part of. You can see there's 19 of us currently and a wide range of individuals. And yeah, with that, I'd like to conclude my talk. This is a little bit of a jumbled conclusion slide, so I'm just going to quickly go through it. If you have any questions regarding the introduction to the technique and the history of microscopes, let me know. I've listed all the important slides here for you to see. If you have any questions about some of the materials from the periodic table, I can go back and discuss those with you, or even the organic molecules and some of the atomic manipulation. And if you want to know more about the lab itself, yeah, please let me know. And thank you for your time.
Thank you, Brandon. That was wonderful. So, so we're going to go through a few of the questions that were posted in YouTube. And if anyone else has additional questions, please put them there in the chat in YouTube. So we'll start with some of the more fundamental questions. One question was, if the STM uses scanning to see the atom, what does tunneling do?
Yeah, right. Okay. So, yeah, the STM indeed uses scanning to see the atoms, but what the scanning actually does is just allows us to create two-dimensional images. The phenomena of tunneling is actually what allows the electrons to go from the sample to the tip. So without tunneling, you could still technically scan, but you wouldn't get any signal. So you need tunneling in order to actually to see the atoms. I also want to say one thing that I didn't quite bring up in the talk, and this is the difference between sort of seeing the atom versus seeing the electrons. We don't actually see atoms. I know that was what the whole talk was about, but what we actually see is the electrons that form around the atoms themselves, and it's this tunneling that allows these electrons sitting around the atom to jump into our tip.
Great. So we had another fundamental question related to tunneling, which was, what are the chances that a baseball would pass through a wall?
Okay, that's a good one. So the chance that a baseball passes through a wall is, I can't say it's zero because it's not, but it is as close to zero as you can possibly imagine, I would say. Because for a baseball to pass through a wall, you would need every single atom of that baseball to tunnel at the same time. The problem is there's only a small probability for each atom to tunnel through the wall. So in order to get all of the atoms to tunnel through the wall, you could probably throw more baseballs than you could actually think of as a number, and none of them would go through. But when you're looking at individual particles, like individual electrons, you don't need this whole coherence of all the atoms to tunnel. You just need one. And that's why this technique works. So I would say even at the electronic level, you're probably getting in a very, very, very small fraction of the electrons actually going into your tip, but it's enough to measure.
Great. Okay, we've got a few more questions that have started coming in. One question is the organic tissue damaged? Is organic tissue damaged when you make this measurement?
Okay, yeah, that's a good one too. So I assume you were referring to the, I'm sorry here. You're referring to the organic molecule here, I'm guessing. It depends. That's a question that really depends on the type of measurement you're doing. So this image right here, like I said, was taken with a slight modification of STM. It doesn't actually quite measure the tunneling per se. And one of the modifications you can make is actually a contact version of this. So if you're actually doing this contact measurement, then yes, you have the possibility of damaging the tissue. But if you're just doing a strictly tunneling measurement, the chances that you damage anything are very small. The biggest issue with these measurements is that the organic molecules are only lightly attached to the surface of your sample. So if you apply too much voltage, you have the possibility of shooting off the molecule into some other part of the sample, and then you have to spend another long period of time trying to find it.
Okay, so this question is from a 10-year-old, Javan, I'm not sure how to pronounce it. Javan would like to know the size of an atom. For example, what would be a good scale comparison? Like how many would fit in the period at the end of a sentence? Okay,
that's a good question. Let me think about that for 1 second to find a good analogy or a good example of the size of a. So I actually watched a video on YouTube while I was making this talk, trying to find some stuff I could use. And I think the best example I saw was that if, I don't know, how do I, no, that's more the nucleus. No, Okay, yeah, if you were to shrink an electron, like the electron is technically point size. If you were to shrink the protons or the inside of an atom to the size of a dime, the actual atom itself would be the size of a football stadium. So that just goes to show you how large they are in terms of the features involved. But the atom itself, I don't really have a good answer to this question. I'm sorry. It also really depends on the atom you're looking at. But let's say that if an atom is 1 angstrom or 0.1 nanometers large, then, and a human hair is 60 micrometers large, then you're looking at, let me just do the quick math here. You're looking at 600,000 atoms in the width of a hair. I think that's actually a pretty good example there. Yeah, I'll stick with that one. So in the width of your typical human hair, there's about 600,000 atoms.
So quite a lot of atoms.
Quite a lot of atoms.
Yeah. Okay, we have a few more questions that have popped up. One is, how do you prepare the surface of the samples without fundamentally modifying them?
Okay, that's a good question. So usually when we're preparing the surface of samples, we actually are trying to fundamentally modify them in some way, shape, or form. In the easiest way, if we're taking a look at, say, a copper sample, you want it to be a really nice flat and clean surface consisting of only copper. But if it was sitting in air, then a lot of stuff is going to sort of attach itself. So what we do is we go through various cycles of what's called sputtering and annealing. So the sputtering part, we take neutral ions, or neutral atoms, sorry, so argon in this case, on the noble metals, and we bombard the sample surface with these atoms, and it basically works like an atomic sandblaster, and it kicks off anything that we don't want on the surface. The problem now is that we get these sort of holes and dips in our sample because we were bombarding it, and it's not even. So what we then do is anneal it, and this is a process where we heat the sample up below its melting point, but above what's called its annealing temperature, and this reorganizes the atoms into nice smooth surfaces. So this is one way of preparing them. Another way we prepare them is by using a technique called cleaving. So if you have a material like my zirconium silicon telluride example here, let me just go back to it. You can see it grows in this layered format. And these orange atoms are only held together very weakly by a certain type of force. If you're interested, it's called a van der Waals force. And this means that if you were to manipulate, what we do is we glue a post onto the top. We literally glue it onto the top of the sample. And we put it in our STM, and then we hit it with a screwdriver. It's literally what we do. It's fantastic, super important research. And what this causes it to do is the sample sort of flakes open, and it reveals an atomically clean surface that was not exposed to air. So those are sort of just two of the ways. I hope that answered your question.
Cool. Wow, so high tech, hitting it with a screwdriver. Right?
Exactly.
Okay, we have a couple more questions here. One is, what kind of pump do you use to create the vacuum in the microscope?
Yeah, that's a good question too, more of an engineering perspective here. We use a bunch of them. So there's different levels of vacuum depending on the pump. So we use what's called a roughing pump or a scroll pump to get to sort of a low vacuum, like a rough vacuum. To put it into numbers, that gets us to about 6 or 7 times better than atmospheres. This is unfortunately nowhere near enough for us to do our measurements. So we have to put this behind, or we put another pump called a turbo pump or a turbomolecular pump in front of this scroll pump. And this turbomolecular pump spins extremely fast. The blades are spinning, so it almost looks like an airplane turbine, just to put it into perspective. And they're spinning at around 60,000 revolutions per minute, if I'm not mistaken, which is ridiculously fast. And this causes the atoms to basically I mean, it works like a fan. They hit the blades, and then the molecules or atoms go into the scroll pump and out of the system. The last pump we use is called an ion pump. This is a bit more. This is for the ultra high vacuum, and this is what gets us to the part where we can actually measure. And it uses two plates that are held at a very high voltage from one another, and it ionizes any remaining atoms and shoots them into a wall of titanium where they just embed themselves and they stick there.
Cool, thank you. So we've got a few more. Oh, so there was a follow-up saying no diffusion pump.
I don't believe we use the diffusion pump on our system, but I can't speak for the rest of the instruments that we might have.
Okay, then there was also a question about what are some applications of your research? I know you talked about some.
Yeah. That's a tricky, honestly, it's quite a tricky question to answer, because I think the stuff that I'm studying, if any applications were to come out of it, you wouldn't see them for about 30 or 40 years. The research I do is quite fundamental in nature, and really comes down to studying the fundamental electronic properties of this whole class of materials, not just one specific material. I know there are some people working in our lab with graphene, which has been sort of touted and oversold as like this end-all be-all material to any problem that's ever arose. It's obviously turned out to not be the case because it's been studied for decades now, or at least a couple decades. But I would say that we don't really have any explicit applications right off the top of my head. It's really just trying to push the fundamental knowledge of condensed matter physics.
Cool. Lots of value in basic research, right?
Exactly, yeah.
So, so what was, there was another question in here. Oh, so there was a specific question. What is the resolution of the scanning step?
Yeah, so that's set by the user, so me. I can set it to as fine or as coarse as I want. And actually, you can sort of see here, let me just get back to an example. So this slide here, you can't see any atoms, right? There is, and this is because the step size is too large to actually resolve an atom. And that's simply because for this material, we don't really care like to zoom in far enough to see the atoms. That's not what we were trying to study here. Versus my zirconium, silicon telluride, for example, where we really did care about what the atoms look like. So the resolution is truly set by the person who's operating the STM. There is a fundamental resolution limit, I guess, of, I think it's 0.3 angstroms. Or no, sorry, it's less than that. No, it's much. No, that's right. No, 0.3 angstroms. Yeah, so about a third of a atom, maybe.
Great, thank you. So that looks like that's pretty much all of the questions that have come in. So I think we can probably wrap up now. So thank you again, Brandon, for a really exciting lecture.
Thank you.
And for kicking off this online experiment in Saturday morning lectures, which I think went very well.
For us, yeah.
So, and thanks everybody for joining us today. So, and we'll have another one coming up, I believe in October is our next one. I don't have the exact date off the top of my head, but check out the Triumph website, and the link was posted in the chat at the beginning, and you'll know when our next lecture is. Thank you.
Okay.